Every quadratic function produces the same basic shape when graphed, a parabola. This is a parabolic shape, right? So if I pick another quadratic function like this one here, it's the same quadratic parabola. It's the same shape. It's been flipped over. So it's concave down instead of concave up. This is concave down. This is concave up. Flipping over a graph is called reflecting. It's been shifted this way and up this way a bit. So we can see it's moved over to this position. And this graph is wider than this graph. So it's definitely got different properties, but the same basic shape, and that is a parabola. Now, it's basically the same. All quadratics can be made by transforming the basic graph or the base graph. So here is the base graph. I'll turn this one off. And the base graph is f of x equals x squared. That's just straight out of the box what a quadratic is. This one here has had some transformations applied to x squared to make it into this format here, which is why it looks the same, but has just been shifted and made wider and flipped upside down. These things are called transformations. Specifically, transformation is the act of changing the inputs, that's the x values, or changing the outputs, the y values, or both, to make a new function. Now, there are three types of transformations. There's heaps of different functions. There are dilations, there are reflections, and there are translations. And in this video, we are going to explore translations. A translation is when every single x coordinate or every single y coordinate has been shifted by a certain number. Let's take a look at a vertical translation. So what I have here is just a whole set of points here. I've got x is from -1 to 5, and the y coordinates here are just effectively what happens when I substitute -1 for x, right? So f of -5 would be -5 squared, which is 25. F of -4 is -4 squared, and so on, all the way along here. So if I turn that on, you'll see, hopefully not surprisingly, that these are just particular points along the parabolic curve. Okay, we know that there are an infinite number of points between these 2 points, for example, and an infinite number of points between these 2 points. I've just chosen these particular 11 points so that to illustrate what's going on. The line, in fact, is really just a merge of every single point. So a vertical translation is when I affect the output, that is the y coordinate, by adding a particular value to every single y coordinate. So in my little sample of points here, I'm going to add 10 to every single y coordinate. I'm not going to touch the x coordinate. I wonder what will happen when I've added 10 to all of them. You can see I've done one here. If you want to, pause the video and think what will happen to the graph when I add 10 to all of them. When I add 10, we can see that those points are all shifting up by 10 units, every single point. But the x coordinates are untouched because we didn't do anything to them. We only affected the y coordinates. And so we can see here that these 10 points here are 10 units above where they used to be. So where it used to be 0, 10, it is now, 0, 0, it is now 0, 10. Where it used to be -5, 25, straight up 10 units, we've now got -5, 35, and so on for every single one of these points. You can see that the shape is the same. It hasn't been made wider or thinner. It is just lifted up in its entirety this far up. Okay. This is just 10 points or 11 points, right? If I look at the base graph here, what I'm doing is I'm adding 10 to every single y coordinate. So I've got my basic function f of x, which is x squared, and I've added 10 to each of these y coordinates. So if I press the turn this graph on now, it should trace through those dot points. As you can see, it does. And every single point in between is now highlighted in red here. So that's y equals f of x plus 10. But we wouldn't normally write it as f of x plus 10. We've effectively taken the f of x, which is the old y coordinate, and added 10 to it. That's what we did there. So let's replace f of x, which is the general y coordinate, with the rule for the y coordinate, which is x squared. So we end up with y equals x squared plus 10. It is a new function, or it's a new rule for the quadratic, y equals x squared plus 10. But it effectively means take the old coordinate, which was generated from x squared, and add 10 to it. And this becomes our new function. Okay, what about horizontal translations? So let me turn off this one, and let's do the same thing but with horizontal translations. Well, let's turn that on. So we're back to just x coordinate minus 5, y coordinate minus 5 all squared, which is 25, and so on. So the dots are along here. But this time I'm going to add 10 to the input. So I'm going to leave the output the same and just add 10 to the input. What do you think will happen? You might have paused the video to think about that, but let's unpack it. Add 10, add 10, add 10. Look at what's happening to these points here. Add 10, add 10, keep adding 10, keep adding 10, keep adding 10, keep adding 10. And now you can see that the function has shifted over by 10 units to the right. That makes sense. Adding 10 will shift every coordinate to the right, but there's no shift up and down because we haven't touched the y coordinates. The y coordinates have remained what they were. So we've just got to shift over to the right, and that's why we call it a horizontal translation. So to translate means to move the points. And just like we did before, if I replace these here and replace these here, and I put a plus 10 in here, what's it going to do? Let's have a look. Oh, it's gone the opposite direction. It's gone backwards 10 units. It hasn't traced those points out. To understand why, let's go back to the points and see. We've got minus 5 plus 10 as our coordinate, but the y coordinate has to be f of minus 5. So how do we get from this coordinate here to the minus 5 here? Well, this coordinate, if we simplified it, is minus 5 plus 10, which is equal to positive 5. So how do I get to minus 5, i.e., so there's no other translation happening, if the x coordinate is positive 5? Well, to get an f of minus 5, I would have to subtract 10 to go back to the minus 5. So it may seem counterintuitive, but in order to make the y coordinate right, I in fact have to subtract 10 from the x coordinate. And by subtracting 10, from the input, from the x input, by subtracting 10, I now have the x coordinate being minus 5 plus 10, and then out comes f of minus 5. So minus 5 plus 10 goes into the function, that's 5. And then I subtract 10 from it to get f of minus 5. So we've got minus 5 goes so we've got minus 5 plus 10 going in. And then, sorry, I'll say that again. When I substitute 5 in here, x equal to 5, I get that. I need f of minus 5 to come out because that's what a translation of 10 units across does. So I've got 5 going in and 25 coming out because 5 minus 10 is minus 5 and f of minus 5 is 25. Okay, so for the x coordinate to translate over by 10 units, I need to be putting into the function x minus 10. Okay, so what does that look like? Well, f of x minus 10, the function is x squared. So what we need to do is we need to replace the old input, which is x, with x minus 10, like so. So So when I replace it with x minus 10, I get it following through the dot points there. Okay, so we've got a couple of different functions here. We've got y equals x minus 10 squared here, which we could then expand to y equals x squared minus 20x plus 100. So we're now getting a sense of a function which is different from the base function, but more or less is just, in this case, a translation off to the right. In the case of a vertical translation, it was a graph that went up or down. Okay, so what does all of this mean in terms of how we might express this in our algebra? So I'm going to just switch over my screen here. And these are notes that you could write down if you want to. So translations is the first transformation we're looking at. It means that f of x, the base graph, has been changed to f of x, what it used to be, plus k. So in other words, if f of x is the y coordinate, then we're going to add k to the y coordinate, and that'll make it go up or down by k units. So for example, f of x equals x squared is the x squared function. So the y coordinate rule used to be x squared, and the y coordinate rule is now x squared minus 2. And we say this as translated by 2 units, and it's minus 2, so it's going to be going downwards. Okay, let's have a look at the next one, which is f of x goes to f of x minus h. Now, this is being a transformation of the x coordinate. Okay, so f is fine, but the x coordinate is now being transformed, and it goes left or right by h units. So if we had y equals x plus 3 all squared, we would say that has been translated 3 units. And if you remember, the minus made it go to the right, so the plus will make it go to the left. 3 units to the left. And that's how you would write it. This function has been translated 3 units to the left. We can also combine our translations. So this one has 2 translations here. We've got this one here and this one here. And we would write them both separately. We would say translated 1 unit upwards, or you could say in a positive direction, vertically, sorry, in a positive direction. And then we would say translated 2 units to the right. So x minus 2 all squared makes it translate 2 units to the right. That will do for this video. The next 2 videos will cover the other 2 kinds of transformations.